Okay, so good morning. Today I've been asked to give a talk on the emerging role of artificial intelligence in reducing radiation exposure in medical imaging procedures. I have nothing to disclose, but would like to acknowledge actually. So, with the financial support of the European Commission under the framework of the Symphonia projects and our associated partners, some of the developments actually carried out in my lab, so linked to this project, which focuses on the use of AI for the development of advanced and realistic computational models and radiation dosimetry calculations in X-ray CT and nuclear medicine were actually developed with the support of this project. So this is not really an outline, but kind of list of topics I'm going to cover. First, start with why do we need AI in medical imaging, and then I will cover the promising applications of AI in dose reduction in medical imaging. So basically, focusing on the items that are listed here, so low dose X-ray CT, path spectrum imaging, image segmentation, and so on. And then I'll summarize this talk and provide future perspectives. Well, artificial intelligence is the ability actually of machines to perform certain tasks which need intelligence showcased by humans and animals. AI was a term coined at Dartmouth College in 1956. And then AI went through a couple of so-called AI winters where progress in the field was criticized and governments stopped actually to fund the research in this area. A major milestone is also in 1997 where IBM's Deep Blue beat the world champion of chess. In 2016, Google's AlphaGo program became actually the first computer Go program to beat an handicapped professional human player. And more recently, 2021, a team that used AlphaFold to repeated the placement in the CASP competition in November 2020, achieving a level of accuracy much higher than any other group. So these achievements obviously are correlated with a number of major milestones in medical physics, including the use of the first LINAC in Stanford in the 50s, so the development of the first position imaging device at MGH in 1954-56, the development of the gamma camera by Anger, thermotherapy by Rockmaki, a number of other major developments, including PET-MRI, CT, the Explore Total Body PET Scanner, PET-LINAC, and so on. There are serious initiatives actually at the European and international level supporting the addition of AI components in existing medical physics curriculum and graduate program, where the AI working group of the FOMP published recently a guideline on curriculum related to AI for the education and training of European medical physicists, and there are a couple of other similar initiatives have taken place in other countries and more worldwide. This is one of the examples actually from recent counterpoint paper that was published in medical physics. So this schematic actually outlines the various tasks within radiology where artificial intelligence implementation is likely to have a large impact. So the workflow comprises the following steps of starting from pre-processing of images after acquisition, image-based clinical tasks, which usually involve the quantification of features, either using engineering features with the traditional machine learning or deep learning, reporting results through the generation of textual radiology reports, and finally the integration of patients' information from multiple data sources. AI is also expected to impact basic clinical characterization of objects in images using segmentation, diagnosis and staging, and the monitoring of objects for diagnosis and the assessment of treatment response. And all of these are obviously are being explored extensively by different research groups. So a recent paper, Benjamins and colleagues provided an insight into the currently available AI or machine learning-based medical devices and algorithms that have been approved by the US Food and Drug Administration, or the FDA. They identified 64 AI or machine learning based FDA approved medical devices and algorithms, and out of these, only 29, obviously 45%, mentioned any AI-based expression in the clinical FDA announcement. So the graph that you see here provides an infographic about the 29 FDA-approved AI-based medical technologies, and most of these technologies were developed in the fields of radiology, cardiology, and internal medicine practice. So getting back actually to the topic for today, so if you check just the example of combined PET-CT imaging, so the effective dose actually the patient receives from the scalp scan, spiral CT, the PET scan are reported here. So basically, so the scalp scan contributes very low effective dose of the patients between 0 to 0.08 millisieverts. The spiral CT, which is the low dose CT scan for attenuation, correction, and mapping, delivers between 0.5 3 millisieverts to the patients, and the PET scan, depending on the activity administered to the patient, so the average is around 4 to 5 or 6 millisieverts. And then a number of institutions perform also diagnostic quality scan with contrast enhancement at the end. Summing up actually the individual effective doses, so we might end up with an average total dose between 20 and 25 millisieverts. So this number has been reduced significantly during the last years, but anyhow, so there was still a number of concerns actually by the professionals and also by the public. For instance, 70,010, so the CT dose was mentioned, so over 2,000 times in the English language media. What's interesting is that a couple of scanner manufacturers, that were Canon and GE, have published a number of white papers recently, and reported on developments of AI-based CT image reconstruction software that has been developed, deployed in the number of clinical centers. So what you see here is basically the true fidelity on the left side and the ACE by Canon on the right side. So obviously both of them reported major improvements in image quality compared to conventional model-based tertiary reconstruction techniques, and Canon also expanded on this development to include also AI-based reconstruction for positional emission tomography. And what you see here is one representative example showing on the left side of the standard reconstruction procedure, including iterative order subset expectation, maximization with point spread function or resolution recovery modeling, and Gaussian post-reconstruction smoothing. On the right side, you see the AI-based solution actually, which is commercially available from Canon. And here what you see is basically quantitative assessment. So the standardized uptake value is still the de facto standard used in clinical setting. You see how values actually produced with the AI-based solution, which might be interpreted as kind of improved resolution recovery. So when using this software, obviously we don't know the ground truth because this is a clinical study. So one of the interesting developments actually that I have surveyed, so for the purpose of this presentation, is this development by Shen and colleagues, so push really the sparsity to the limits. So you know that you're familiar with the principles of topographic imaging, which requires a certain number of projection views from a large number of angular positions to be acquired to produce artifact-free volumetric images. And so this scientist from Stanford showed that a deep learning model, trained to map projection radiographs of patients to the corresponding 3D anatomy, can subsequently generate volumetric X-ray series images of the patients from a single projection. And these are some of the representative examples they have provided in this article, where they demonstrated the feasibility of the approach with upper abdomen, lung, and head and neck series scans of 3 patients. In another study, actually, so carried out by our lab, so we aimed to design an ultra-low dose CT examination protocol using deep learning approach suitable for clinical diagnosis of COVID-19 patients. So in this work, so we used 800, 170, and 171 pairs of ultra-low dose and full dose CT images as input and output for training tests and external validation tests, respectively, to implement the full dose prediction technique, and with the residual convolutional neural network to generate a full dose from ultra-low dose CT images. And the quality of the images was predicted by radiologists who assessed basically the images, so giving scores from 1 to 5, and then we use also a number of quantitative metrics to assess the quality of the images. So obviously we did not scan the patients twice for ethical reasons, so we developed a simulation code that generated the low-dose CT scans from the corresponding full-dose CT scans. And this is one of the examples showing you the chest CT of the one of the patients, full dose. This is the low dose, which obviously increased the statistical noise, as you can see here. And this is the predicted full dose scan with much improved noise properties. So obviously similar to the full dose scan that you see on the left side. And another example here, see the full dose, the low dose again, and the predicted dose. So the same observations can be made with respect to image quality and noise reduction. But what we observed actually from the clinical interpretation of the radiologist is that this is an outlier. And the reason is that one of the COVID-19 lesions, so basically the patchy lesion, was converted to consolidation. And the red rows actually point to these changes in the identified lesion. So clearly this is an outlier where the AI-based solution did not provide the expected outcomes or failed to provide the expected outcome. This is another study, basically, with the busy slide showing the flow charts adapted to assess the additional radiation dose associated with overranging. So major problem actually in X-ray CT scanning. And the aim of this work was to develop an automated scan range selection technique using deep learning to reduce the radiation dose to the patient. So first, the 3D long masks were generated by a neural network, and then the 2D projected localizer images and masks were computed in lateral and anterior posterior directions, and we developed a deep learning method to predict the long masks and the scan image ranges on both 2D images. So this segmentation procedure was developed actually in previous work in the context of segmenting the lungs and the COVID-19 lesions. So we've just used it actually in the framework of this development, the COVID-19 lesion segmentation framework. So the results now, so our scanning was has occurred in 99% and 95% of the cases in the superior and inferior directions, respectively. And moreover, so the extent of overscanning in the inferior direction was significantly larger. And the plots that you see here, so basically show the additional radiation burden in terms of organ doses in milligray and total body effective dose in millisieverts to patients due to over scanning in both directions. So the evaluation of a large multicentric chest CT data sets revealed obviously a necessary effective dose of more than 2 millisieverts per scan and 67% increase in the thyroid absorbed dose. So significant overscanning also range between 31 millimeters was observed in clinical setting for over 95% of the cases. So by considering the exact lung coverage as a ground truth and AP and lateral projections as input, the deep learning based approach resulted in errors close to 0.008 millimeters and minus 1.5 millimeters in the superior and inferior directions, respectively. And more importantly, so this plot shows basically the performance of a deep learning network compared to human range selection. So commonly carried out by the technologies for the outlier cases, and all challenging cases had vague or vague inferior boundary patients presenting with severe pathological conditions. So in another study, we used also the Brownian techniques to reduce patient dose or acquisition time, as the two were obviously correlated. So the objective here was to assess the performance of standard dose or full dose PET image synthesis in the image and the projection domain from PET images and low dose sinograms or projections without sacrificing the quality of diagnosis using deep learning techniques. And the data were acquired in list mode format, which made it easier actually to decimate the data to generate sinograms corresponding to a portion of the acquired data, in this case 5% of the acquired events. And without further delay, so this slide here displays the cross-sectional coronal sagittal views showing the PET reference full dose, low dose, and the predicted images, so in both image space and in the projection space. So the low dose image corresponds to either the injection of 10 megapixel of FDG or the equivalent of the full dose that's acquired in very short time, so just one minute acquisition time overall. So the overall conclusion is that these are just the bias maps actually comparing so the reference image with the predicted images and the low dose images, and the conclusion is that the prediction in the projection space produced much better results compared to the predictions in the image space. And this was also the outcome of the clinical validation step for the assignments of scores by qualified or experienced nuclear medicine physicians. So we see here that the scores were close to 4.1 on average for the predictions in the sonogram space compared to 4.47 for the full dose images. And we also performed a quantitative assessments using blunt L1 plots where each data point reflects a brain region. So obviously aligned all the images to the Hammersmith atlas, which contains 83 brain regions, and through the SUV bias is extremely low for the low dose images, so the increased variance compared with the full dose images, and it was observed actually reflecting so poor image quality that was obviously well handled by the AI-based solutions, and obviously the predictions in the sonogram space provided their outcomes. So extended this work actually, because what we did not do in the previous paper is that we did not include the time of flight information, which obviously explodes the data size of the sonograms. What we did in follow-up study that was published in Your Image, and using so statistical parametric imaging. So what we see here is basically this reduced significantly. So the differences or statistically relevant differences voxel-wise between the predictions in the sonogram space compared to the predictions in the image space. So basically, so confirming the previous results, but highlighting also the importance of the including time of flight information. So encouraged by these results, we pushed this further to a full total body of whole body imaging. And we used also a couple of neural networks, so basically modified cycle generative adversarial network called SIGAN, and the residual neural network, or called ResNet, instead of using synthetic low dose images that we did in the past. So the patients in this case were acquired twice, and the difference between the two, so there is a factor of 8 difference between the full dose scan and the low dose scan. So without further delay, you see here, so basically a representative study with the low dose CT scan, the full dose PET scan corresponding to an acquisition time of 3 minutes per bed position, the low dose scan corresponding to 25 seconds per bed position, and the predictions by the residual network and by the cycle GANs. And then also we asked a number of nuclear medicine physician colleagues actually to interpret so the images, and we splitted the whole body images into two zones, so basically focus on the brain and head and neck area, and then the thorax and the abdomen. Again, so similar to previous conclusions. The quality of the predictions with the cycle GAN was much better compared to the residual network approach. And an additional step that we have conducted in the studies that we asked also our microdisciplinary colleagues to look to the lesion detectability and to count the number of lesions actually they are seen on both the low-dose scans, the full-dose scans, and the predicted images. And we actually separated the regions according to their metabolic activity. And the outcome is basically what you see here is that cycle GAN missed only a very small number of lesions, so basically 4 compared to 23 for the residual network, and obviously the low-dose scan produced very low scans and missed a significant number of lesions. Just to show you, so one of the examples here, so this is one of the patients with basically clinical study with multifocal multicentric breast cancer with the skin involvements of the right breast and extensive lymph node metastasis, including the mediastinal nodes, comparing the full dose and low dose images, as well as the synthesized images using both networks. What you can see here is that the lesion in the inferior quadrant, so the long red row, was detected on the full dose, low dose, and both neural networks, but the mediastinal lymph node actually that you see with the highlighted or pinpointed with the short red row was visible on the full dose, and was not visible on the low dose and residual network, but was visible only on the full dose and on the cycle GAN. So in a follow-up study, would also focus it in cardiovascular SPECT imaging, where we aim to investigate the feasibility of dose reduction in SPECT MPI scans without sacrificing diagnostic accuracy. So deep learning approach was proposed against to synthesize the full dose images from the corresponding low dose images at different dose reduction levels in the projection space. And what you see here is that clinical SPECT MPI images of representative studies. So we're showing the standard dose scan, the half dose scan, then the 1/8 dose scan, and the prediction, the corresponding predicted images. And the conclusion of this work is that the noise was effectively suppressed by the proposed network, and the predicted standard dose images were comparable to reference dose scans up to quarter dose levels, obviously. So the 8th dose did not produce images that were of diagnostic quality. Another area in which our group has developed some expertise is the development of anthropomorphic imputation models, and this work was obviously done manually, and this took a few weeks to a few months of difficult segmentation work. And the idea here is to automate the process by developing AI-based solutions, and we focused on pregnant patients, where the idea is to develop a deep learning model which is capable actually to segment the pregnant patients, including the fetus, and using a very simple architecture using pairs of X-ray CT images and the manual annotations performed by an experienced radiologist. So you see here the outcome, the original CT images, the manual segmentation in the middle, automated segmentation on the right side of the SCC better on the 3D illustrations here, so showing the coronal and sagittal views of the model generated using manual and automated segmentation techniques. Again, so a very good agreement between the manual segmentation and the automated segmentation performed by the deep learning solution. So our colleagues also in radiation oncology are shifting towards MRI guided treatment planning for a number of indications where the soft tissue contrast provided by MRI outperforms the information provided by the X-ray CT, but X-ray CT is still needed for the radiation dose calculation part. And the idea here is to suppress the need for an X-ray CT and to develop AI-based algorithms that enable to generate pseudo-CT images directly from the MRI. And we conducted actually an exhaustive comparison for conventional segmentation approaches or pseudo-CT generation approaches from MRI with a deep convolutional neural network that was at that time produced or developed by Electra, which is a company producing MR-Linacs, and also other software for radiation therapy, and obviously also Linux. And the outcome of this comparison is that the deep learning network produced much better results compared to conventional techniques reported in the literature. So encouraged by these developments, we developed a method called adversarial semantic structural learning, which contains two generative adversarial cores, one for CT image synthesis, what we see in the upper part, and semantic structure extraction, which is shown here in the lower part. So the CT synthesis and semantic structure cores are composed of a pretty large number of layers, and the network consisted of over 54 million trainable parameters. Without further delays, show you see this the outcome here. You see the MRI in the line of CT and the MRI segmentation procedure, which is implemented on the Siemens PET-MR machine, which basically segments the MRI into single tissue components actually for the brain if you are in the thorax region. So there is also lung as an additional tissue class, which was not realistic at all. And you see that the deep learning framework provides really very good results. Even the skull is highlighted and depicted here, the nasal cavities. And obviously, if you look to the bias maps on the PET images, so the segmentation, MRI segmentation is not a very good solution for this type of applications. Another framework that has been explored recently is to get rid of the X-ray CT scan and to train a deep neural network actually to transform or to convert the attenuation corrected images directly to attenuation corrected images. And we did this for a number of applications, including neuroimaging for a number of tracers, as you can see here. So comparing here the X-ray CT and the CT-based attenuation correction and the segmentation-based approach that I described in the previous slides. And the deep learning network did a very good job in all four tracers that were explored. And we also explore this type of applications for attenuation correction whole body PET imaging. And the important outcome here is that contrary to CT-based attenuation correction, which might have issues in the case of mismatch between X-ray CT and the PET scan, so the deep learning network is able actually to solve this problem because it's not influenced by the CT, as you can see in this example here. Just for the sake of time, so the largest application I'm going to describe here is internal dosimetry, which is obviously carried out in a clinical routine using simplistic approaches, including the MIRV approach, which was developed in the late 60s and beginning of 70s. And we came up with an interesting approach that enables actually to map the inert depositions voxel-wise. Just for the sake of time, I'll show you a couple of examples here. So comparing the Monte Carlo based approach with the voxel-wise S-values approach proposed by the MIRV and the multiple S-values approach published recently in Journal of Molecular Medicine. And obviously, so the outcome is that the deep learning approach produces much better results compared to the conventional approaches. And similar techniques are being devised also for X-ray CT dosimetry voxel-wise. And this is one of the articles describing these developments, and I encourage you to go through this paper if you're interested actually to explore the power of deep learning for voxel-wise CT dosimetry. And the last thing that I would like to mention here is federated learning, which is an important development in my opinion, which enables basically to pull data coming from different centers without the need actually to get access to the clinical data. So instead of getting access to the clinical studies, so we share the models, and each center is capable to train so the model, and then we get back to the waste to the server, and then run the AI-based solution. And we have used this type of federated learning techniques for a couple of applications, so pattern image segmentation and attenuation correction successfully. A number of interesting guidelines have been published by different bodies, including RSNA, radiology, medical physics, and more recently the Society of Nuclear Medicine. These are very important guidelines that need to be followed. Actually, when writing scientific papers reporting on AI-based solutions. And skip again, so the summary for sake of time, and this is the take-home message. So was nice citation by Professor Ingrid Dava. She is from Duke University. Machine learning works quite well, and we don't know why it works so well. So we consider that a challenge for mathematicians to understand it better. And I believe that if something works, there is a reason, and we have to find the reason, right? So with this, I thank very much so my team and the funding bodies actually supporting our research. And I thank you very much for your attention. Thank you so much.